The last part in igneous petrology includes basically petrography and petrogenesis of different kinds of rocks. Before we jump onto that part, I would just like to revise the very basic stuff that we already know, basically all the way from ultramafic to felsic rocks. Okay, so and some examples of those. So for example, in ultramafic rocks we have peridotite, in mafic rocks we have gabbro and basalt, intermediate diorite and andesite, and finally felsic rocks are granite and rhyolite. So the ones that you see on the top are the plutonic ones, that is which crystallize inside the earth, and these are volcanic, means they crystallize after erupting onto the surface of the earth. Okay, so the mineralogy, this is why I'm discussing this basically in different types of rocks that are there in the syllabus. Some of them basically, whenever you have to write in, for example, usually the topic is petrography and petrogenesis. Okay, so in petrography, if there is some texture, you have to write about it, but you also have to tell about the mineralogy. What minerals do you find in that rock? Okay, so for example, if you're asked about petrography of granite, so you know granite is composed of orthoclase feldspar. So this is what we have in here. So this is for this composition of rock. So here you see silica content is higher on the left hand side because felsic rocks are rich in silica. They also have high amount of potassium and sodium. Mafic rocks are rich in iron, magnesium, and calcium. Okay, and they have more higher melting point. These have lower melting point, or they start to crystallize at higher temperatures. These will crystallize at lower temperatures. So if you want to find out the mineralogy of granite, for example, if you have orthoclase feldspar, quartz, plagioclase feldspar is more sodium rich. So this is the sodium rich part. On this side, you have more calcium rich, and then you can have biotite, muscovite. Okay, so and then amphibole. And this tells you what percentage of mineral. So it is quite rich in orthoclase feldspar, quartz, and a little bit of plagioclase, not as rich. So for example, if your composition is here, so 100 to 60 means for this amount of silica, almost 40% is orthoclase feldspar. On the other end, if you have, let's say, basalt, so basalt is rich in plagioclase and pyroxenes, and this pyroxene is actually of two types, so you can think of it like sort of like in this way. Okay, so you have clinopyroxene, which is formed at slightly lower temperatures, and orthopyroxene, which forms at slightly higher temperature. So basalt is a rock, for example, if you have to write mineralogy, it is rich in plagioclase feldspar, which is more calcium rich. It has clinopyroxene and orthopyroxene. Okay, so plagioclase plus CPX plus OPX. Now if you go to ultramafic rocks, now ultramafic rock is basically olivine plus OPX plus CPX. So instead of plagioclase over there, you'll see more olivine. Okay, so ultramafic will be CPX, OPX, and olivine. Okay, intermediate rocks, they're rich in amphibole minerals, maybe biotite and plagioclase, feldspar, and possibly very, very little quartz may also be there in these intermediate rocks. Okay, so they're intermediate between mafic and felsic rocks. Another thing that you remember is mafic and ultramafic rocks are dark in color, whereas felsic rocks are light in color. Okay, another way to look at some of these rocks is to look at the alkali content. Okay, so these are the alkalis, okay, in the rock, and this is the silica content, weight percent SiO2. So silica content is increasing on this side. So what we just covered here, okay, in this figure, it just looks at the silica content, but if you also plot Na2O content here as well, okay, so usually you can just draw this diagram, okay, like this. So you have Na2O plus K2O, that is total alkalis, and on this side you have SiO2, and just draw a random line here. Basically on top of it you have alkaline rocks, and these are subalkaline rocks. Okay, means they have less alkali content. So here that boundary sort of like goes like this. Okay, so it's actually going to somewhere middle like this. Okay, so the rocks, for example, basalt, andesite, rhyolite are the ones which you saw here. Some minor classification in between. So you have, see, for example, rhyolite has more silica content and basalt has less silica content. If let's say it goes to even more mafic, you have picrobasalt, or dacite is in between andesite and rhyolite, and then you can have basaltic andesite. So here the names are fine. Again, you don't need to memorize it. I'm just telling you basically what is of alkaline and subalkaline rock. Okay, some of these rocks will be there in syllabus. For example, phonolite could be there. Okay, or trachyte, trachytesite. So you just should know that these are the rocks which have higher content of alkalis in them. Okay, but the main important is this one you should remember. Now we will start with different types of rocks. Okay, so granite, you know, is a felsic rock. It is derived from word granum, which means grains. It is a coarse grain rock. Okay, so this is the part of petrography only. Coarse grain felsic rock, SiO2 is greater than 65%. Essential minerals are the minerals which will like almost always be present. Okay, accessory minerals may or may not be present. So quartz and feldspar, albite, which is basically Na-rich plagioclase. Okay, and K feldspar are the most common types of feldspar in this rock. Accessory minerals will be biotite, muscovite, amphibole, zircon, magnetite, pyrite, etc. You don't need to remember all of these. Whatever names you can find easier to remember, just write that, and you've seen already here. So some, even in this category, some biotite, muscovite, and amphibole may be there. Okay. Now petrogenesis. Petro means rock. Okay, genesis means formation. One more thing I just want to tell you, that they have interlocking texture. This you can write this word interlocking texture in whatever igneous rock comes to you. Okay, because igneous and metamorphic rocks have interlocking texture. So you can write this point in all these rocks. Another thing you will usually find is, okay, so this word coarse grained. Okay, so this word coarse grained, because most of the rocks that are given in syllabus are coarse grained only. They're not given fine grained rocks. So this also you can blindly write. Usually this petrogenesis, how these will form. Okay, so magma, major source of magma in earth is basically mantle. But if you melt mantle, okay, mantle is actually mafic in nature. Okay, sorry, ultramafic is ultramafic in nature. If you melt it, you actually get a basaltic rock, which is mafic in nature. So how do you actually get a felsic rock? Okay, so felsic rock you can only get, so please remember, melt, when you partially melt a rock, okay, again this, let me write partial. Okay, so the melt is always more silica rich than the parent rock. Okay, because silica and this potassium, sodium, they are all incompatible elements, means they want to go into the melt stage. Mafic components such as iron, magnesium, calcium, they want to stay in the solid phase. Okay, so to get granitic magma, so mantle cannot melt to give you granitic magma, because mantle will give you basaltic magma. So crust itself will have to melt. The crust would be basaltic crust, intermediate crust, okay, or granitic crust. So crust has to melt. Okay, or if it is mantle, melt. B, it has to be highly evolved. What do you mean by highly evolved? Highly evolved means this basalt, let's say is there, basaltic magma is there. Due to crystal fractionation, mafic minerals could be preferentially removed so that the residual melt which is left, it can keep on becoming more and more silica rich. But for both these processes to take place, for it to evolve, it needs more time and space, so that the magma keeps on rising and rising and rising and keeps evolving. Oceanic crust is usually very thin, so it does not provide that much of time for crystal magma to rise, that much of space, and for it to crystallize. So usually this part that you see in here, okay, so it requires thickened crust. Okay, so granites are associated with events of crustal thickening. These could be due to orogeny. Okay, so it could be either continent ocean convergence in case of, for example, Andes Mountains. So there you can get basically andesitic intermediate volcanism also. You can get basaltic also, or you can also get granitic. Okay, so many times associated with these subduction zones, you will see granitic magmatism. And another is continent-continent collision. So that can also result in crustal thickening. If crust gets thicker, so the rocks at the bottom, they may become hotter, and there may be some melting, partial melting. So granites. So in Himalayas example, you see what is called leucogranites. Okay. All right. Now granitoids. What are granitoids? These are granites and associated rocks are called granitoids. Okay. So as per IUGS classification, so this is, you may not write it in your answer on petrography and petrogenesis of granites if it is, let's say, a 10-mark question. But if it is 15-mark question, okay, or sometimes they may ask you specifically, okay, just this part. What is IUGS classification of granitoid rocks? So it is not perfectly granite, okay, but these are granitic rich rocks, okay, more felsic rocks, which will be plotted on this one, okay. So you saw here in granite, okay, so the main components are orthoclase feldspar, quartz, and plagioclase feldspar. So based on relative compositions of these, you can have different types of granitic rocks. So this part, for example, if they ask you about composition of granites, okay, or composition of granitoids, if they ask you about, so here, for example, now this becomes a composition of granite. Let's explain this. Or if they ask you about granites only, petrography, petrogenesis, and composition of granites, then you have to write this or draw this diagram. If it is not a 15-mark question, it is a 10-mark question, then you can skip it. But in a 10-mark question, they can ask you just to draw this diagram. Okay. So in this diagram, what do we have? We have quartz on this side, plagioclase, and alkali feldspar. Okay. So the names that you see in here, okay, they may appear a little bit complicated, but it is not that complicated. So everything that I have drawn in red here, those are the only names that you need to memorize. The rest of those are basically sort of like you can automatically get from these names. So you have quartz, alkali feldspar, and plagioclase. So granites, first of all, you know, anything which is plotting here is quartz rich and it is poor in alkali feldspar and plagioclase. Okay. So this rock that you see in here is mostly quartz rich. Okay. So if this is 90 here, so it has more than 90% quartz and less than 10% alkali feldspar plus plagioclase combined. Okay. So this is very easy to remember. Quartz rich is quartzolite. Okay. Granite has basically a little bit more alkali feldspar than plagioclase, so that is why it is in this half. It is shifted in this half a little bit, and it has basically quartz is also there and feldspar are also there. So this region that you see here is actually granite. So if in the exam they ask you about granites, still you can draw this diagram and say that compositionally granite is this rock. So it does not take that much of time. Please practice drawing this diagram once or twice, okay, because this is important. But overall, you just have to practice drawing these 3 or 4 lines, and this is quartzolite, and then you can say that this is granite. Okay, so once you practice 2-3 answers in this one, this diagram you'll be very comfortable with this diagram. So this is what granite actually is. Okay. Now, just you need to remember 2-3 more names, which are actually not very difficult because again, cyanite is there in your syllabus. So you may be getting composition, petrography, petrogenesis of cyanite. So you can still draw this diagram and highlight that cyanite is over here. So cyanite is a rock which has very little quartz, okay, because it is away from that quartz corner. It is mostly alkali feldspar rich. It may have some plagioclase, but that is also very less. So usually less than 10% to 20% plagioclase. So this cyanite is alkali feldspar rich rock. So if cyanite comes in the exam and you draw this figure and you highlight this and write that alkali feldspar rich rock, cyanite is alkali feldspar rich rock, so you'll get it over here. Okay, and you'll see this in the next part as well. Okay, so granite is done. So the next is cyanite rock. Okay, so petrogenesis diagram I've drawn here because I ran out of space in here to make it more clear. So cyanite, as you see, you can use the same figure and then highlight composition of cyanite is over here. Okay, so its mineralogy in petrography, when you're writing its mineralogy, it will be rich in alkali feldspar. Again, interlocking texture, it is pore grained. All the rocks that you're going to study are pores. Or you can write phenolitic and interlocking texture. So these 2 keywords you can write in all the rocks because these are igneous rocks. Okay, so now how does cyanite develop? Okay, now cyanite is alkali feldspar rich rock. It means it has very high amount of potassium, and let's say alkalis Na could also be there. So these are incompatible elements. Okay, and one thing to remember about incompatible elements is, okay, so they will form in 2 ways. Okay, so if you have, let's say, a mafic, ultramafic rock or mafic rock, okay, if you melt it, okay, if you melt this rock, okay, so let's say if you melt the complete rock, okay, let's say this is ultramafic, if you melt the entire thing, because of law of conservation of mass, this will also be ultramafic. Okay, but if you are to melt very little portion of it, okay, now this part will be concentrated in incompatible elements. Okay, and this is ultramafic. Now there is very little partial melting. So one thing that you have to remember is lower the amount of partial melting, okay, lower the amount of partial melting, higher will be the concentration of incompatible elements. Because as you enrich this part in incompatible elements, this will keep on getting depleted. So the more melting will take place, so the melt is coming from depleted ultramafic rock. Okay, but this is just to say that 2 things that you have to remember is lower the degree of partial melting. I will write it somewhere. Okay, in a new slide. Please remember this part: lower the degree of partial melting. It means richer in incompatible elements. Okay, the same thing, more evolved magma means, after magma is formed, then it will start to crystallize. So the crystals will keep on getting removed. The remaining magma, the residual magma, is called evolved magma. So it is also richer in incompatible elements because they want to stay in the liquid phase. So all the compatible ones are removed in the crystals, but these incompatible ones are remaining in the melt phase. Okay, so please remember this much. Now in cyanite, you see this sodium and potassium are incompatible. They want to stay in the liquid phase. So this rock will develop in those cases where the degree of partial melting is very less. So this figure tells you how you may get cyanite. Okay. So as I told you, in subduction zone, many different kinds of rocks can form. Okay. So here this is the mantle, asthenospheric mantle, which is convecting. So if your magma is generated here from mantle, because mantle is ultramafic, okay, so it rises to the top, okay, and basically it forms this basaltic melts. And also you see it is at the center where convection is taking place. So temperature is highest here. Okay. So higher temperature means more melting. More melting means it is not rich in incompatible elements. So you will get basically it is more mafic in nature. Okay. Now, if the again mantle is melting, but it is away from the convecting axis, so the degree of partial melting is less. It means the melt is more rich in incompatible elements. Now you see, if the continental crust itself is melting, okay, if the crust itself is melting, then you will get granitic melts in those cases. Okay, so for cyanide, you have to focus on this thing. Another part is you can just draw this diagram to show cyanide, so which will be there in the next slide. Okay, so you can use this diagram QAPF to highlight that this type of rock is cyanide, which is alkali feldspar rock. So it is a coarse grade intrusive rock that is rich in alkali feldspar but poor in quartz. Volcanic equivalent of cyanide is trachyte. Okay, so volcanic equivalent. So these in this figure, all these rocks were volcanics. So you can see here, trachyte is this rock. Okay, so this rock. So you can see here, it is above this line that I've drawn. It is rich in Na2 and K2O, and it is felsic in composition. Okay, so that is why we drew it in granitoid rocks. Less than 5% quartz in petrography you can write. Rich in orthoclase feldspar, less than 10% plagioclase feldspar is there. Biotite is rare. Apatite and zircon may be present. Okay, most of the aluminium is taken up by orthoclase. Orthoclase is K feldspar, KAlSi3O8. So most of the K feldspar has gone in orthoclase. The per alkaline in nature means they have high proportion of alkalis in comparison to aluminium. Petrogenesis, they form in thin continental crust or in subduction zones. They require very low degrees of partial melting to get high concentration of incompatible elements, and they also form due to plagioclase fractionation. As I said, fractionation also results in evolution of magma. The next rock type is diorite. Okay, so in this figure, okay, I was explaining this figure. Let's continue with this one. So as I said, you don't need to remember all the names. So you already know granite and cyanide. Okay, these two. Now there is another rock which is called diorite and gabbro. So this is diorite is intermediate. Okay, it is coarse grained equivalent of andesite. Okay, and this gabbro is mafic in nature. So based on this QAP diagram, you cannot differentiate between them because it does not involve pyroxene minerals. This is for granitoid rocks. Okay, so in both basaltic and intermediate rocks plot here, basically they are rich in plagioclase. They will also have amphibole, orthopyroxene, okay, clinopyroxene, but they are not in this triangle. We do not plot them. So you will have a different triangle for these. But in this QAP triangle, these rocks plot over here. Okay, so now you know that the next rock type, diorite or gabbro, plots here. Okay, so this is another red one. Just remember a few more. You have monzonite here. So monzonite is again quartz poor rock, but monzonite has roughly equal amounts of alkali feldspar and plagioclase feldspar. Cyanide is rich in alkali feldspar and has less plagioclase feldspar. Monzonite has roughly equal amounts, and both are poor in quartz. Okay, so once you remember this name, and the final that you have to remember is tonalite. Once you remember these names, the rest all are in between them. Okay, so for example, this is quartz rich granite. So it is between granite and quartz, so it becomes quartz rich granite. Now this granite is rich in alkali feldspar, so A is over here, so it becomes alkali feldspar granite. And this is cyanide. Okay, so it is even more rich in alkali feldspar, so it becomes alkali feldspar cyanide. It goes a little bit above, it has more quartz, so it becomes alkali feldspar quartz cyanide. Okay, so because you're moving towards quartz in this direction. Okay, similarly, this is quartz cyanide, quartz monzonite, quartz monzodiorite, and this rock is monzodiorite in between monzonite and diorite. So it is also easy to remember. The rock between monzonite and diorite is monzodiorite. So please draw this diagram. You will automatically understand the pattern which is there. So diorite here is mentioned. It is this rock. Okay. Now diorite is intermediate rock. So this means it is between mafic and felsic. And you know that mafic rocks are dark in color and felsic rocks are light in color. So here you will have both dark minerals and light minerals. And this texture that you will get is called salt and pepper texture. Just as salt is white in color, pepper is black in color. So it will appear that mixture of white and black colors. They are not like forming gray, but they are present as separate grains. Okay. Mineralogy, plagioclase, amphibole, pyroxene, and you have already seen this in here. Okay. So for diorite, this is the rock here. So you have some quartz may be there, but it is very minor. Here, the main is you have plagioclase feldspar, you have amphibole, some pyroxene may also be there in these rocks. Okay. Petrogenesis, diorites, they usually occur as large intrusions as dikes or sills within continental crust. So for example, if this is a dike which is intruding the surrounding rocks, they are many times made up of diorites. Okay, often these will form above convergent boundaries. Okay, where an oceanic plate subducts beneath continental plate. So it is very similar to basically, as I said, in subduction zones you can get many different rock types. So one of them is diorite. If it erupts on the surface, it will form andesite. So intermediate rocks are very much characteristic of subduction zones. Okay, so this is one is easier to remember. Partial melting of mantle due to volatile flux. So we have drawn this figure so many times in subduction zones. Okay, so this volatile flux, this water which is being added when it melts mantle, in this case it produces mafic magma. Now this mafic magma, when it rises up, it assimilates with granitic crust. So this crust, for example, let's say in case of continent collision, okay, so this crust is granite and this magma which is coming is mafic. When assimilation takes place, you will get intermediate magma. Okay, if the magma erupts, you get a rock which is andesite, otherwise it is diorite. Okay, so this is the diagram for diorite. Okay, what you're seeing here is that felsic crust assimilates into mafic magma. So this is the crust part, and this is the lithospheric mantle. Means it is mantle, but it is rigid in nature, so we call it lithospheric mantle. So here magma rises up at this boundary, it starts to accumulate, and then you can get basically diuretic magma. Okay, if it crystallizes in the earth only. Then you have basic rocks. Okay, basic rocks or mafic rocks are rocks with a relatively high concentration of iron, magnesium, and calcium. Silica content is 45 to 53%. So in granite it was more than 65%. Here it is less. So here in classification, okay, because you see they don't have too much of alkali feldspar and quartz, so we base the classification based on plagioclase, pyroxene, and olivine. Okay, so these mafic rocks that you see here, okay, so gabbro or basalt, as I said, it is plagioclase plus OPX plus CPX. So basically OPX and CPX are both pyroxene minerals. So it is a pyroxene and plagioclase rich rock. That is why gabbro and basalt are compositionally similar. Only difference is gabbro is coarse grained, basalt is fine grained. Okay, a rock which has pyroxene and olivine, okay, it is called plagioclase bearing ultramafic rock. Okay, so here if it has up to 10% plagioclase. Usually I told you, for example, mantle composition. Mantle is made up of a rock which is called peridotite. Okay, it is OPX plus CPX plus olivine. Okay, so it is pyroxene plus olivine rock. If some plagioclase is there, so it is not really mafic rock, it is an ultramafic rock, but you call it plagioclase bearing ultramafic rock. If the amount of plagioclase is even more than it is not ultramafic, then it remains mafic rock. Then you call it olivine gabbro. So basically gabbro does not usually have olivine, but in this case you call it olivine gabbro. A rock which is mostly plagioclase and olivine means it has very little pyroxene, then it is called proctolite. And a rock which is rich in plagioclase, and plagioclase in basalts will be calcium rich. And you know that the calcium rich variety of plagioclase is anorthite. Okay, in terms of petrography, basic rocks which are exposed are usually extrusive, therefore fine grained. So this coarse grained thing that you're writing, so in case of basalts, basically they extrude. Okay, so coarse grained rocks, okay, usually are very rare to find on the surface. Why? Because these are usually formed at mid-oceanic ridges. Okay, so on the surface you will find basalt because it is extrusive. Okay, and here you will have gabbro, but you see this gabbro never comes to the surface, it goes back into the mantle, so it is consumed. That is why they are not very common exposures. The only places where you may find those exposures are what is called ophiolites. Ophiolites are abducted ocean crust fragments. So let's say there is on this side of the subducting plate, if there is a continent, if this plate is subducting like this, and on this side there is a continent. Okay, so this is moving on this side, so later on, let's say on this side also you have continent, so later on these continents will collide with one another. Okay, so in between this oceanic crust which was present, let me draw it in red, this crust which was present, some part may get squeezed in between. This is called abducted ophiolite. Okay, so it is oceanic crust which has been, abduction is opposite of subduction, so which has been thrust on top of continental crust. Okay, so only in these places you have exposures of coarse-grained mafic igneous rocks. Mineralogy: plagioclase plus orthopyroxene plus clinopyroxene plus minus means amphibole may be present or absent. Similarly, olivine may be present or absent, and the rocks are dark colored. Okay, petrogenesis: these kind of basalts you can get basically almost in all places. So you can get these at mid-oceanic ridges. So where the type of basalt is called thoriites, and their example is mid-oceanic ridge basalt. MORB stands for mid-oceanic ridge basalt at divergent boundaries. Ocean island basalts, they form above hotspots. Okay, so this is the core mantle boundary here, from where your mantle plume is rising up, and this will result in eruption of basalts. So for example, in Indian example is Deccan basalts and the Deccan plateau. Okay, so they erupted due to hotspot activity. Now there are others which are alkaline and calcareous in nature. Okay, so they're called calc-alkaline basalts. They are found in subduction zones. Okay, the next is ultramafic rocks. Okay, ultramafic rocks, they are igneous rocks with very low silica content. Okay, usually it is greater than 18% MgO, high FeO, and low potassium. So they have less than 45% of silica. Earth's mantle is mostly composed of ultramafic rocks. So in classification point of view, so peridotite is the general name for a rock of mantle. Actually, peridotites are basically rocks which have pyroxene plus olivine. Okay, so plagioclase is not there. Now these peridotites can be of three types: Hasbergite. Okay, Hasbergite is orthopyroxene and olivine rich. Leusolite has basically OPX plus CPX plus olivine. So this is the standard peridotite. And if the rock is rich in olivine and clinopyroxene, so less orthopyroxene, it is called bearlite. Okay. The rock which has very little olivine but mostly pyroxenes, it is called websterite. Okay, so this is the name. These rocks are called pyroxenites because they're pyroxene rich, there's less olivine. So all these rocks here are called pyroxenites. So olivine. Now this rock that you see here, it is called, because it is rich in orthopyroxene, this is called orthopyroxenite. This rock is called clinopyroxenite. Okay. And if some olivine is present in orthopyroxenite, it is called olivine orthopyroxenite. If olivine is present in clinopyroxenite, it is called olivine clinopyroxenite. And in websterite, if some olivine is there, it is called olivine websterite. Okay, so this is classification of ultramafic rock. Hasbergite, leusolite, bearlite are types of peridotites, and olivine orthopyroxene, olivine websterite, and olivine clinopyroxene are types of pyroxenite, and we also have websterite, orthopyroxenite, clinopyroxenite. Okay, they are rich in dark minerals. Olivine, orthopyroxene, clinopyroxene are the main minerals. Dunites is a rock which has over 90% of olivine. So this is a dunitic rock. They, in terms of petrogenesis, they usually occur as layered intrusions. Okay, they're found in mantle. Comatites are extrusive types of mafic rocks. As mantles, they occur as mantle xenoliths and crustal rocks as well. Now next one is anorthosite. Anorthosite. Okay, this is a slightly strange rock. Okay, because anorthosite is rich in anorthite. Okay, and anorthite is basically calcium rich plagioclase, which is really actually this may form at high temperature, but it is a felsic minerals because it has high amount of SiO2. Okay, so in terms of composition, they are closer to felsic rocks, but based on temperature and based on, let's say, they have mostly calcium rich plagioclase, they are actually closer to, in terms of genesis, they are more closer to mafic rocks. Okay, so they have more than 90% of plagioclase, and you saw this in this diagram over here. So this rock that here, which is rich in anorthite, is called anorthosite. Okay, so this rock that you see in here, 90 to 100% plagioclase, less than 10% is olivine, ilmenite, magnetite, pyroxene. Okay, this is highly felsic but related to mafic rocks. There are no volcanic equivalents of this rock. It does not erupt to the surface. It is grayish or bluish in color because of plagioclase. Calcium rich plagioclase is bluish or grayish in color. K feldspar, okay, is more orangish in color. Okay, so in terms of petrogenesis, they are derived from magma under plating. They are derived when magma underplates the crust. So basically, sorry, underplates the crust. So this is crust, this is mantle. So mantle derived magma is basically sort of like underplating is coming up and setting just under the crust. Okay, so I will explain it to you in the basically simpler figure if you cannot draw this figure. Okay, anorthosite is a very simple to explain in terms of petrogenesis. Let's say this is your magma chamber. Okay, so in this magma chamber, what is going to happen is, okay, so what you're going to get in the magma chamber is, so let's say this is the magma chamber. So when fractional crystallization is taking place, let's say some of these blue minerals are forming. Okay, what will happen is they will try to, usually these are lighter than the mineral. Let's say this is plagioclase. Okay, this is plagioclase minerals, and they will rise to the top and they will accumulate on the top. Okay, if there are any heavier minerals in this rock, they will settle to the base. Okay, so the lighter minerals, this is lighter than magma. Okay, these ones which are heavier, they will sink at the bottom. So not many minerals are heavier than magma, so are lighter than magma. Most of them are heavier. So on the top, most of the minerals that will accumulate are plagioclase only. So this rock which will be formed at the top will form anorthosite. Okay, they will rise to the roof of the magma chamber, and at the base where you get those cumulate textures. So for example, this could be pyroxene. Okay, so they will settle to the base. So these are heavier. Example, pyroxene. Okay, they will settle at the base. So that is how you'll get this. So here basically the same thing is shown to you. It's just a little bit more complicated figure, showing that this takes place in between crust and mantle. But overall process is similar. These are the heavier minerals which have been settled at the base, and on top you have these lighter minerals which have been accumulating, and some partial melting of overlying crust may also take place. Okay, so all these are plagioclase minerals which are these circles, and these are mafic minerals which are settling at the base. The next rock types are alkaline rocks. Okay, as I've already explained, if you draw this figure of Na2 and K2O and weight percent silica here, okay, so the rocks that you get here which has less Na2K2, they are called subalkaline. For example, you studied basalt is a subalkaline rock. Tholeiitic basalts are subalkaline rocks. So the alkaline rocks are basically the main ones that you have to phonolite. Okay, this is the same figure which you saw in the very first page. This one. So I've just drawn this much part of that rock. These are all alkaline rocks. Okay, so within these alkaline rocks, what do you observe? So these here you have basalt. They're very basic in nature, so they're called basanites. But they have more Na2 and K2 than basalt. Okay, then you have tephrite. Okay, and this is phonolite. So these are the only three names which you have to memorize. In between you have phonotephrite, which it is tephrite only but phonolytic in nature. This is tephrophonolite, so it is mainly phonolite but tephric in nature. So these are the main rocks classifications of these rocks, and the main examples are the ones that you see here: phonolite, tephrite, basanites. They usually lack silica phases. Okay, silica phases I should write. Quartz is usually not found. Quartz you will find. Okay, what happens in igneous rocks is, so you have SiO2 and you have other cations, Na2O. Actually, this is SiO4 4 minus. Okay, which is silica cation. So it will combine with Na, K, Al, Fe, Mg. All these elements are present in the magma. So they will all combine with silica. Now, if after this some silica is left, after combining with all this, so then you get SiO2 free phase. So these are called silica saturated rocks. Now, in case of alkaline rocks, that amount of Na and K is so high that no free silica is left. So these rocks will not have quartz. Okay. So Na2 and K2O, okay, more Na2 than what can be accommodated in feldspar. So Na2O is also greater than not just silica but also greater than Al2O3. Okay. They have high titanium content as well. Petrogenesis majority alkaline rocks as we studied in case of cyanide as well. So cyanide for example was rich in potassium, feldspar, potassium and sodium. So these are also rich in potassium and sodium. So they are incompatible elements. So they will be generated by low degree of partial melting. Very low degrees of partial melting, and cause of melting could be degassing of mantle or evolution by crystal fractionation. So incompatible elements can also be concentrated by evolution of crystal fractionation. Okay, degassing is the process by which gases escape from the magma. Okay, the next part is a carbonatite rock. Okay, carbonatite rock is a little bit similar to kimberlite. Okay, so this kimberlite rock is an ultramafic rock. The name comes from Kimberley town in South Africa. Okay, and the most important part about these rocks is that they're rich in diamonds. Not always, but they may have diamonds in them. Okay, and similarly for carbonatite. So these are alkaline igneous rocks composed primarily of carbonate minerals, calcite and dolomite. Okay, so name comes from carbonatite. They contain rare earth ore minerals as well. Petrographically, more than 50% carbonate minerals such as calcite and dolomite, commonly altered hydrothermally by phenatization. So hydrothermal alteration is kind of like a retrograde metamorphism. So at slightly lower pressure and temperature, if you have these hot waters which are circulating, so they may change the rocks. So olivine, for example, may be converted into a clay mineral called sericite. So that's called hydrothermal alteration. If you don't remember this detail, it is okay. Okay, not that important. Olivine, pyroxene, naphthalene, and feldspathoids are minor constituents. So these minerals that you see, especially olivine. Okay, olivine, feldspathoid. This mineral naphthalene is an example of feldspathoid only. Okay, so these minerals are silica undersaturated. These are silica undersaturated. What does it mean? Means they have less silica. Okay, then they can actually accommodate. For example, olivine phosphorite is Mg2SiO4. Okay, if you want, okay, so you can actually take it SiO2, you can add SiO2 to it to give you Mg2Si2O6, which is a pyroxene mineral. So you can think of olivine as pyroxene minus silica. Similarly, for example, if you have albite, which is feldspar, which is NaAlSi3O8, you can subtract one silica from it. So this is feldspar mineral. So you can get NaAlSi2O6, which is a feldspathoid. So feldspathoid is feldspar minus silica. Petrogenesis point of view, so petrogenetic understanding is not well developed for carbonatites. They occur close to other alkaline rocks and ultramafic rocks. There are three models: direct generation by very low degree partial melting in the mantle, low liquid immiscibility between carbonatite and silicate melt. So liquid immiscibility means as temperature is lowering, a melt can separate out into two different melts. Okay, so one of the melts will be silica rich, another one will be carbonatite rich, or you can have what is called extreme crystal fractionation. The next rock type that is important is Charnockite. It is named after statue of Job Charnock. Okay, he was a British official, and this his statue, I think it is in Kolkata Museum, is named is made up of this rock. Okay, which is very common. It is actually not even an igneous rock. It is actually a metamorphic rock. Okay, so basically in this rock, what we have is orthopyroxene bearing quartz feldspar rock formed at high temperature and pressure, commonly described as orthopyroxene bearing granite. Okay, so it is actually belonging to what is called granulite facies. Means very high grade metamorphic rock, and this is the main part: orthopyroxene and quartz. Usually you do not find this mineralogy. It is not very common. If you remember in the first page itself, okay, here in this picture. So orthopyroxene is somewhere here. Okay, quartz is somewhere here. So there is no overlap. So it is not a rock which is very usual. Okay, it is actually a metamorphic rock. Okay, commonly so which is orthopyroxene bearing quartz feldspar rock. Okay, all charnockites were once thought to be igneous, but most are metamorphic now. Okay, petrographically they are granular like granite, so it belongs to granulite facies in metamorphic petrology. Quartz, so you'll study, if you have not gone through this part, so you will understand this term better when you are studying metamorphic petrology lectures. Okay, so just keep this in mind. Or you can basically cover charnockites after you have covered metamorphic petrology, and there is a topic in metamorphic petrology that is granulite terrains of India. So you can go through that topic and then come back to this one. Now, from petrogenetic point of view, charnockites are high grade metamorphic rocks that belong to granulite facies. Okay, temperature is greater than 800 degrees Celsius. Okay, charnockite problem. Okay, basically is a problem. Again, we will discuss this in metamorphic petrology. But granulite facies, okay, what happens is once you have pressure and temperature, okay, this is the wet granite solidus. It means after you cross this line, melting will start. So usually granulite facies occur here. So if the granite is there, wet granite, so for example, it should start melting. And wet means it does not mean that it has to be soaked in water. Even minerals in their crystal structure, such as mica and amphibole and clay minerals, they can have water in the chemical structure. Okay, so during metamorphic reactions, when the rocks are getting buried, that water can be released during metamorphic reactions. These are called dehydration reactions. Again, you study them in the metamorphic petrology part. So water can come from there. So this Charnockite problem actually includes these two parts. First of all, how were such high temperatures achieved at large scale? What caused it? Okay, and why did the rocks not melt at those high temperatures? Okay, so the solution possibility to this Charnockite problem is probably CO2 played an important role by reducing activity of H2O and prevented melting, and heat supplied by magma underplating. So magma could have risen up, which could have supplied the heat over large scale. And what happens is, what is this CO2 activity? So let's say if you have this rock is there, okay, this rock is there. Inside that rock, let's say there are some fractures in which this fluid is present. Okay, so now if carbon dioxide is also present in the system, let me draw that in black. So that reduces the activity of water, so which can prevent melting of rocks. Okay, or you can write the next point as well. So these were essentially, please remember, dry conditions.